Hello, everyone, and welcome to today's SANS webcast. When your forensic tool only tells part of the story, finding code injection using memory analysis. My name is Carol, author of SANS, and I will be moderating today's webcast. Today's featured speaker is Aaron Sparling, officer with the Portland Police Bureau in Portland, Oregon. If during the webcast you have any questions for our presenter, please enter them into the questions window located on the GoToWebinar interface at any time. Please note that this webcast is being recorded, and a copy of the slides and recording of this webcast will be available for viewing later today and can be found on the SANS registration page. And with that, I'd like to hand the webcast over to Aaron.
Thank you, Carol. Good afternoon, good morning, good evening, wherever you are where you're watching this. Thank you for tuning in. Like the title says, we're going to talk about what to do when your tool kind of only tells you part of the story when you're looking at code injection and analyzing memory analysis. So real quick, like Carol said, I'm an officer with the Portland Police Bureau. I'm assigned to their digital evidence, digital forensics unit. I've been with that unit for about 8.5 years. And during that time, I've sat on a couple different task forces, the FBI Cyber Task Force, the United States Secret Services Electronics Crimes Task Force, and I currently chair the Technical Advisory Council for the United States Secret Service National Computer Forensic Institute, also known as the NCFI in Hoover, Alabama. And I'm also an alumni of quite a few SANS courses. So let's just sort of get right to it. What's the end game? So what are we going to do over the next 50 minutes or so? Luckily for you guys, there won't be a whole lot of slides. We're going to briefly sort of loosely define what is code injection, mainly just for the purpose of this webinar, so you can sort of contextually have an idea of what we're doing. I'll talk real quick and brief about some of the tools that will be used for analysis during the demos. But the bulk of this presentation, the bulk of this webinar is going to be in the hands of the demo gods. Seeing that it's 2020, I figured why not? What else could go wrong? So we are going to walk through 3 different memory samples. The first 2, I kind of classify those as being easy wins. So this is where we'll go through a workflow that's associated with kind of my analysis process, and we'll see where the tool works for us, where the plugins that we invoke are actually kind of telling us the complete story, and in some way sort of packages it with a bow. The third one is really the thesis of the whole webinar, and that's what do we do when our tool is trying to tell us something, but we're not quite getting the complete picture. And so the tool puts it back in the lap of the analyst to dig a little deeper and ask a few more questions. So like I said, we'll loosely define code injection just for the purpose of this webinar. So essentially it's the act of injecting code, in our case malicious code, into the memory address, the virtual memory address of a targeted process, and then executing that code within the context of that injected process. And yes, it's kind of a mouthful, but the next slide will really kind of break that down a little bit more in detail. There are numerous types of code injection. Probably the 3 most recognizable to folks are the ones listed here, which is like DLL injection, or commonly referred to as remote DLL injection. The other one would be reflective DLL injection when we're dealing with things like shellcode, where shellcode will be loaded into the virtual address, memory address space of a process, and then might call a malicious DLL. And then the other one, which we won't see demoed, but people definitely recognize the term, is hollow process injection or process hollowing. So what's the recipe for code injection? And this is a very generic recipe. I realize that there's different ways to do this, but again, to just sort of frame it for this webinar, the first thing we have to do is obtain a list of the active running processes. So if I'm the malware or the malicious binary, I'm going to see what's running on the system. Then I'm going to obtain a handle to that process, or the process that I want to inject. And in this case, we'll just pick on explorer.exe. And then I'm going to suspend explorer.exe so that I can allocate a portion of its virtual memory. And then I'm going to move or write my code or move my malicious code into that allocated memory space. And then I'm going to resume that process. And that, in essence, is one form of code injection. So like I said, the bulk of this is going to be in demo land. The entire demo is going to be done inside the Remnix virtual machine. There'll be a link at the end in the reference section where you can go if you're interested in downloading this virtual machine. This is a virtual machine that is developed and maintained by Lenny Zelster and his team. And Lenny, if you don't know, is the course author and course lead for the SANS DFIR 610, the reverse engineering malware. The tool that we will predominantly be using inside of Remnix for our memory analysis will be Volatility. And again, I figured 2020, we're doing a demo, let's just go all in. Let's just go ahead and use Volatility 3, even though it's still in beta. There'll be a small little section of code analysis, and for that, I'm going to use Red Array 2 or R2. And then for deobfuscation, there'll be a short little demo utilizing CyberChef. And all of these tools are linked in the end in the reference section if you're not familiar with them and want to go download them. They're free. They're all free and open source. So with that said, let's jump right into the demo. So I've moved over here to my Remnix virtual machine. And the first memory sample that we're going to take a look at, we're going to, I'll just show you my command line invocation that I've kind of preloaded. So I'm calling Volatility 3 up top. I'm saying run it against my memory sample, which is this front one.lime. Render it in the pretty mode, and I want to run the PS list plugin. But instead of seeing all of the active processes that are running on the system during the time of the acquisition, I want to just grep for the presence of service host or SVC host or Explorer. And the reason I'm doing this is because over time, I've come to realize that these two processes are commonly picked on when it comes to code injection. So we run the tool and we see that, yep, we got a bunch of service hosts. And over on the left, you're going to see the PID, the process ID for each process. And then right next to it, you're going to see the parent process. And in this case, the parent process is 676. If we were to look further, we would recognize that that is services, which is the right parent for SVC host. And then as we scroll down, we're going to see our first instance of Explorer. And then we go down a little bit farther in the bottom three processes, we see two more service hosts. However, what stands out to me with them is they don't map back to services. They map back to something other than services. And then we see another instantiation of an Explorer at the bottom. That in and of itself is not malicious, but it might be a little suspicious. So I'll slide over to this column here. I'll highlight it. This is the session ID column. And since we have more than one Explorer, we should have, each one should be assigned its own session ID. And in this case, they're both given the same session ID of 1, which is anomalous. Then you'll also notice that with these last two service hosts and this bottom Explorer, they all match in the true column for being 32-bit. So these are 32-bit processes running on a 64-bit system. So that in and of itself is a little bit interesting. So we're going to pivot on just one of these. We're going to pivot on the SVC host of a PID 424. And what I've done is I've already preloaded it because it takes just a minute, but I have dumped the virtual memory address space of that particular process. And I've dumped it into this directory called memdump. And if we take a look inside this directory, we're going to see that you would use the memmap plugin and then dump it to this directory. We're going to see that it basically has dumped the entire virtual address space for process 424 and given us a single dump file. The second thing that I did was I ran the floss tool, which is it's a great strings-based tool that is provided by the folks from the Flare team from Mandy at FireEye. And there's actually a really good SANS DFIR Summit presentation that you can find on the SANS YouTube website on this tool. But I ran floss against this dump file and created a text file that we can now search for or search through. And so the first thing I'm going to do, which kind of seems a little counterintuitive, is I'm going to run the strings command against my output file, and I'm looking for strings that are larger than 1,000. And when we do this, we see we get a lot of output. But what I'm going to do is I'm going to scroll up to the top. And when we do that, you'll notice here that I see a reference to a web inject 32, and then I see some stuff that looks like it's possibly base 64 encoded. And then right below that, I see a reference to VNC 64, and again, I see something that might be base 64 encoded. So finding that to be kind of interesting, let's pivot on that. So what we're gonna do is we'll grep for web inject against our text document. This kind of narrows it down, and here is our base 64 encoded data, or what we think might be base 64 encoded data. And we can copy that and move over to CyberChef. So I'm running CyberChef from inside the browser, inside the Remnix virtual machine. And I'm gonna paste this into CyberChef. And you can see I've already asked CyberChef to decode this from base 64. And I see what looks like the presence of a portable executable file by the magic value of MZ. But we can validate that or continue to sort of look at that more by sliding over and seeing, well, hey, we have like what might be a DOS stub. And then just looking a little bit farther in this deobfuscated data, we see a reference to PE, and then we also start to see references to what might be legitimate PE header sections, right? Like the read-only data, the data section, the text section, and the relocation section. The next step that we might want to take is like, we might want to know more about what's going on here. So we can dump this to an output file by just naming it whatever you want and dumping it. I've already done that for the sake of the demo. And if we look over here in the CyberChef directory, I did it for both the web inject and that VNC 64 that we saw earlier. And if we run the file command against these dumped sections that we decoded using CyberChef, we see that with the file command, it recognizes that the VNC 64 is a 64-bit DLL and the web inject is a 32-bit DLL. So we're starting to see right away, like, well, there's some interesting things going on here. I want to know kind of more about this. So if we shift back over to where we started grepping through our strings, our floss text file, we'll notice not only with this web inject that we're grepping against, we also start to see a reference to a domain. And so if I clear my screen and we grep this domain inside of our text file, we're going to get a fairly robust output. But we scroll up to the top, which only takes a quick second. We're going to notice that we've got this domain, and we see reference to web inject. We see reference to maybe a config file. We start to see this long string here, starting with the number 1. We see a data file, but now we see something that's a reference to maybe an executable, right? So we've got something new to pivot on. We've got this executable file right here that it's referencing. And we want to know a little bit more about what's going on with this particular executable file. So I'll clear my screen out here. I've copied that over, and we're going to use volatility again. Oops, we want to get out of this directory. And we're going to take volatility, and we're going to try something new. We're going to see if we can't try to locate this particular file. So what I'm doing here is I will give you guys the lowdown of my syntax. Is I'm telling volatility to run the Windows bad Yara scan plugin, and I'm saying -- Yara -scans, and then giving it the string that I want it to look for. Oops, I'm sorry. I want to change this to rules. Already off to a great start. -- Yara -rules, and then I'm going to give it the string that I want it to look for. And in this case, it's going to look for just this particular string as a single rule. Now, if I had Yara rules that I wanted to run against it, I could do the -- Yara -rule and point that at a YAR file. And because this is scanning across the entire memory range, it takes a little over a minute. So we'll just kind of use this time to recap what we've done thus far. So the first thing that we did was we used Volatility with the PS list plugin, and we said only show us instances of service host and Explorer. And we were able to quickly identify 2 suspicious service hosts and 1 Explorer. We decided to go ahead and just pivot off of the service host 4224, and I dumped the entire memory address space for that particular process. Then I ran the floss tool against that dump file, outputted that to a text file, and then we ran strings against it looking for large sections. And instantly we noticed a reference to a web inject and then maybe some code that might be obfuscated. And just by looking at it over time, you could kind of start to get an idea like what may or may not be base 64 encoding. So we pivoted off of the web inject and we grepped against the text file for that. And we found a smaller data set that we then copied that encoded data, threw it into CyberChef, decoded it using a base 64 decoder, and saw what we thought to be presence or signs that point towards a PE file, a portable executable file. So we went ahead and dumped that out, and then we ran the file command against it. And in fact, files listing that to be a Windows DLL. So moving back into where we were looking at that text file, we also noticed that by grepping web inject, we saw a reference to a domain. And then when we grepped that domain, we saw a reference to this executable. And again, we're just running the volatility framework again, now against our memory image, and we're saying run the vad scan against our entire memory dump, looking for this particular string. And so when this is done, hopefully soon, it will point to hopefully some indicators that we can then continue to pivot off of. And if for some reason this hangs, I can just kill it and we can jump forward from here. I'll give this just another second. There we go. So it's finished. So what this output is showing us is it's showing the virtual offset here on the left, where it has found this string in memory and then the associated PIDs. In this case, we see 4224 and 4268, which are PIDs that we are familiar with. However, we've just been introduced to 3 new PIDs that we've not seen before. So let's take a look real quick and see what those are, and we can do that by using the PS list plugin. And telling it to look, just tell us about these particular processes. And now we can get an idea of what we're dealing with. And in this case, they're all 3 chrome.exe. Well, that's kind of, that's kind of interesting. So let's pick on one of these and we'll pivot on one of these particular processes. And in this case, since we're dealing with code injection, we're going to use the malphine plugin, and we're going to say, just show me or just scan process 5100, which we know is a chrome.exe. But I also want you to do a couple things for me when you're doing that, because I want you to grep for the presence of a MZ header and show me 1 line before and 7 lines after. And when we do this, we see that, okay, chrome.exe using the malphine plugin, which is a plugin that is used to look for, the big thing that we'll focus on here is permissions. And it's looking for VADs that are set to a page execute read write. There's a few other things that it's doing, but for the purpose of this demo, we're going to focus on the page execute read write. It also gives us a little bit more robust output. We see that it's flagged on the presence of an MZ header, and we can confirm that with the 4D5A hex values here. And it's saying this memory address, this virtual memory address within chrome.exe, that we have a VAD short, so we have a short memory range where that section, those VADs are set for page execute read write. Well, let's validate that. We don't just want to believe everything that our tool tells us. So let's validate that by looking at vadinfo. And we're gonna do the same thing by giving it PID 5100. And we're just gonna say, is the presence of this address set to page execute read write? And it is. So now we want to know a little bit more about what's going on, because we just see the presence of an MZ header. So let's just dive a little bit further into this to kind of validate that, yep, our tool is telling us what it should be telling us. And we can do this by using vol shell, and I'll talk about this in just a sec. Let me get this typed in. So for those of you that are more familiar with Volatility 2.6, you'll know that vol shell is a plugin that's inside the Volatility framework. With Volatility 3, it's kind of its own standalone framework. So you call it outside of Volatility. And in this case, the syntax is very similar. I'm using the -F for the file I want it to read, which is our memory file. The -W says treat it as a Windows operating system, and then drop me into the current context of process ID 5100. And we can see here that, yep, it's reading as Windows. It's dropped me into the current the current context of process 5100. And now what we can do is we can say, hey, let's take a look at what's going on inside this memory range. Oops. So what I've done here is I've said, display the bytes at this virtual address and show me basically the next 1024 bytes. And we see the MZ header, which malphine showed us, but we also get to see a little bit more, right? So we see the DOS header, and then if we dive down a little bit further, we start to see the read-only data, the text section, the data section. These are all sections within a PE header. So great. So we know our tool is telling us a complete story. So let's take another memory sample and do something very similar. But now we're just going to jump right into malfind, right? So malfind is our plugin. And in this case, we're looking at a separate memory image. And we know that, hey, malfind is pretty aggressive and can potentially find us the presence of an MZ header. So let's see if it works in this case. So by grepping for an MZ header, and we're going across the entire memory image. So malfind is scanning across the entire memory image. It's saying, check for all VADs that are set for page execute read write. It's doing a bunch of other things, but we're just gonna stay focused on that. And if you find one that's page execute read write, then check to see if there's a presence of an MZ header. And because this is a scanning plugin, they take a little bit longer and nothing's found. Well, that's not all is lost. We also said with like reflective DLL or reflective code injection that sometimes they'll use shellcode to do its evil bidding. So one of the things that we can do is we can look for the presence of a no-op or a NOP sled, which is a hex value of 9090 and a bunch of them usually in a row. And so what we're doing here is we're doing the exact same thing. We're saying, hey, let's use malfind, scan across our memory image, and grep for the presence of a no-op sled or a NOP sled. And so it's currently doing that now. Again, it's a scanning plugin, so it takes just a couple seconds. And because we're also asking it to do some grep. And we get some output. And we'll notice that at this memory address, we see a no-op, and then immediately following it, we see another no-op. So that is super interesting to me. And because we picked on SVC host in our last example, we'll take a look at Explorer in this one. So now I'm saying, hey, malfind, I see that we found the presence of possibly a no-op or a NOP sled. What about scanning across the entire memory range and seeing if there's anything that comes back that's interesting with Explorer? And in this case, spoiler alert, it's going to come back and Explorer is going to hit on this particular plugin, and we'll be able to continue to pivot off of that a little bit more.
Hey,
So,
excuse me, Aaron, this is Carol.
Yes.
We're wondering if you can make the font a little bit larger.
Yes, let's see if I can do that. Did that work?
Okay, that looks good for me. Let me know if you'd like it to be larger, attendees who are viewing. Thanks, Aaron.
Okay, yeah, sorry about that, guys. Sometimes I forget. It looks probably much smaller on your screen than it does on mine. Okay, so we can see that, yes, in fact, malfind, when we grep for Explorer, we found the presence of Explorer. And we'll notice that we have a PID, a process ID of 6824. Our process is Explorer. And we have a virtual offset or a virtual address where that particular VAD sits that's set at page execute read write. And if you notice, that virtual memory address happens to be the same virtual memory address that we got with our no-op. So now we have we have more to pivot on. And again, we're not just going to take the word of one tool. So we're going to check our work real quick. And we can do that. I'll clear my screen to make it easier for you guys to see. We can do that again with the vadinfo plugin. So we'll do the vadinfo plugin. We know a PID now, which is 6824. That speeds things up significantly. And we'll grep for that particular virtual address space or that VAD address offset and see if it is flagged page execute read write. And it's just one more way for us to kind of check our work as we move along. And sure enough, we get a return hit for that. So now we want to see what's going on at this particular address space. So we're going to drop back into VolShell. And we have to give this the -W as well because it's a Windows system. And then we want to jump into the current context, of PID 6824. Oh boy. Syntax matters. There we go. Okay, so now we're going to drop into this particular context of this PID, and we can do a little bit of investigation on it. So the first thing I'm going to do is I'm going to do the same thing. I'm going to display some bytes, and we're going to go back up to and just make sure we grab our offset. Scroll back down, paste that in. And in this case, I don't need to look super deep into it, so I'm only going to look, my count is only going to equal 256. And when we do this, we see, remember I said the hex value 9090 sometimes is indicative of a no-op sled, and then we see a bunch of hexadecimal, which I personally cannot translate into assembly, but you may be able to. So luckily for us, inside VolShell, we can do a little bit of disassembly. With the DIS command or the disassembly command, we can ask it to take a look at that and disassemble it. And when we start to look through this disassembly, we start to see things like the no-op sled or a possible no-op sled. We see reference to a 64-bit register, which is the instruction pointer register. We see, values being moved into registers. We start to see some conditional jumps. We see some XOR stuff. So we start to reasonably believe that we are dealing with some possible shellcode. But we can go one step further. We'll make a directory. We'll call it malphine. And then what we're going to do is we're going to dump this section. And one of the unique things or interesting things about working with Volatility 3 is you have to put the dump directory before the plugin. So what I've done here is I've just said, hey, let's use malfind. We're going to dump the sections that malfind found into our directory. Well, I didn't spell malfind right, but it's going to dump it into that directory. I'll clear this out. We'll cd into my misspelled directory. We'll take a look, and there are our dumps. So now what we can do is we can just, by using a disassembling tool that's built into Remnix, Radair2 or Radair2, however you wish to pronounce it, we can take a little bit deeper look into this dump section and see if it's interesting or if we would want to maybe pass this on to like a reverser. So what I've done here is R2 is how I would call Radair2. I'm basically saying look at it as x86, 64-bit, and let's take a look at what we got. And so you can see here that this tool has done a little bit of interpretation beyond what we were able to see in VolShell. And this is where we would be able to go and pass this on to our reversing team, or if you are your reverser, you now have a dump file that you can reverse and work with. So again, we were able to use malphine to quickly get to what we reasonably believe to be code injection, and it was by all intents and purposes pointing us in the right direction and showing us everything that we thought we needed to see. So I will make that bigger. So now let's take a look at another memory image, our third memory image, and this is going to be the one that sort of aligns with the whole purpose of this webinar. What happens when our tool is pointing us in the right direction, it's telling us something, but we're not getting the complete picture. So again, we're going to jump right into malphine, and since we grepped the first time for an MZ header and the last time we had success with no op, let's just kill two birds with one stone and see if we can't just grep for them simultaneously and see if we're able to score a big win. So we definitely find a couple presents of the hex 90 value or a no op, but they don't sit on top of each other, so they're not indicative of what we might think to be a no op sled. Well, that's okay. Well, let's dig a little bit deeper into this. So going back to picking on our favorite processes, Explorer and Service Host, let's see if we have any luck with these guys. And basically what I'm saying here is if you find it, show me the 8 lines after the hit, and that's what the capital A8 is. And so here we see a couple instances of Service Host, of SVC host, and if we scroll down, we see PID 164 service host, a 1232 service host. This is the same Explorer, and then we have another SVC host. And if we notice, we've got data in here, but we have no presence of an MZ header or what might be a NOP sled. We have no data here. In the Explorer, we have some data and a little bit of data here. If you can see my cursor moving, hopefully you can. And then we continue to scroll down, we still see a little bit of data, but we don't see the presence of an MZ header, and we don't see anything that looks like a no-op sled. However, if you notice with process 1232, we see the absence of data. And sometimes I find that the absence of data can be as telling or more telling than the presence of data itself. So I found that to be a little anomalous and a little interesting. So I thought, well, maybe we should dig a little bit deeper into this particular process, and specifically at this memory address, and see what's going on at this memory address. And the way that we can do that is, again, using VolShell. So, oh, I did it again. If you can't hear, I have an English bulldog that wants to be let out really bad. So here we're going to drop into this particular process, and we're going to look at some disassembly. And we're going to disassemble from that, from the virtual address that malphine was pointing to us. And we're going to say, hey, let's look at the first 1,000 bytes, basically, and see what we get. And when we scroll, when that comes through our screen, we basically get nothing. So let's clear that out, and let's just jump to the end and see if the end of this frame or the end of this page in memory has anything to show for it. And it doesn't. So I got to this point and I was like, well, this is super, super odd and very uncommon. So we'll grab this last address, we'll clear this out, and let's see what happens if we jump into the next section of memory, or the next frame, if you will. And when we do that, we start to see some stuff that looks like legitimate assembly code. And if we were to take a little bit deeper dive into this and start to display some of the bytes, we would actually be able to find the presence of an MZ header. Give me 1 second. I've got to let this go. Never fails. Okay, so we're going to go back to malfind, and just like before, we're going to dump that section, and we are going to say, oops, we need to make a directory first. So we're going to ask malfind to dump this particular entire section to a dump file so that we can now start to look at that and maybe figure out what's going on. So we'll cd into our malfind directory, and there is our dump file. And if we were to run the file command against this dump file, it's just going to tell us that it's some data. But luckily for us, there's a hex editor that's baked into the Remnix VM that will allow us to open this up and take a look at it. And we can search for the presence of an MZ header. So I've already pre-cooked this with the 4D5A, and we find it right here. So I'll highlight it so you can see it. We've got what we believe to be the presence of an MZ header, and we can see the DOS stub. And then if we look a little bit further, we can start to see the sections within the PE header itself. So what I want to do is I want to know, can I extract this, right? Can I carve whatever this is from memory, from this dump that I got from malfind? So we're going to delete everything above our 4D5A, and then we're going to save it, and we'll just call it 1232.bin. Why not? And then we'll close out of our hex editor. We'll say no, Control, and we'll look in here, and now we have this fresh new bin file. Now we can run the file command against that and see what it says about it. And it's telling us that we have file is reporting it back to be potentially a 32-bit DLL. If we want to know a little bit more about this, clam scan is also baked into the Remnix VM. So we can run clam scan against this binary to find out a little bit more about it. And again, spoiler alert, it is going to come back as malicious, and then we'll be able to pivot just a little bit more on it. So recapping, we used malfind. Malfind was not pointing us to the presence of an MZ header. It wasn't pointing us to what might be shellcode, but it was definitely telling us that there was something going on with that particular VAD. And so we had to drop into vol shell to interrogate the first page or the first frame. And again, we saw nothing, there'd be nothing but zeros in there. Because we know that there's malware out there like CoreFlood or Conficker that is known to wipe out the header of a malicious binary or zero it out. That's what I initially thought was going on, but it looks like it just wrote it into the second page of the second frame. So we see reference to a virus to the mortar worm, and I've got a little write-up that's already been done on it. So doing a little bit of OSINT, we can see that this particular malware has some embedded passwords. It leans heavily on run DLL32.exe to run as admin, and that it also might be AV aware, that it might have some stuff in it where it does some AV checks. So just like everything else that we've done in our workflow, let's just real quickly see if we're on the right track. So we can run floss against our malicious binary, type that out to less, and we can kind of do a quick little static analysis to look through some of these strings. And the strings that I'm interested in are just to validate that, yep, I'm looking at a sample that ClamScan has identified as the mortovirus. And again, we see this run DLL32.exe, run as admin. Well, we got that from our OSINT output, so we're probably on the right track. And then we start to see stuff that looks like passwords. You know, there's some classics in here like the I love you. There's probably going to be a password with a capital P. There's going to be a log me in or let me in for sure, because why not? And then we scroll down a little bit further, and we will start to see references to antivirus engines. So here we see actually FreshClam, which is part of ClamScan. We see a bunch of different companies' antivirus titles in our strings output. So we can surmise that, yep, we have gone through and carved out and extracted a malicious executable, or in this case, a DLL that was injected into memory. So let me just recap what we did and why this last one I think is so important. If we were to just run the malphine plugin, and I'll show you. So if we were to just run the malphine plugin against our PID, and we're not going to dump it, this would be our output. And if we just ran malphine against the entire memory image, we might get, you know, 8 or 10 different processes that give us some sort of output. Like I showed earlier with the other service hosts and the other Explorer. And it's easy, I think, for newer analysts or folks that are newer to doing malware analysis, especially memory forensics, to just skip past this and bypass this and ignore it because there's no data being presented. And that's the huge takeaway here. So again, to kind of like wrap up the whole thesis of this presentation is this is our tool telling us something, but it's not giving us the complete story, right? We're not getting the 4D 5A up here like we're used to seeing, right? We're not getting the presence of an MZ header, or we might not be getting the hex 9090, the presence of maybe like a no-op sled where we start to pivot onto shellcode. All we're getting is a tool that's saying, hey, wait a minute, there's a section or there's a VAD region, in this case, from here to here, that's flagged page execute read write. And so just by taking a few extra steps, utilizing vol shell, we can quickly start to see, is our tool reporting what we think it's reporting? So with that, I know that was kind of a lot, but that is the presentation.
All right, thanks for that great presentation. We do have some questions ready for the Q&A. However, if anyone has a question for Aaron, please enter it into the questions window now. The first one asks, what is the best way to investigate rootkit and find attacker's malicious driver?
Yeah, that's a whole, it's like I was only dealing with process memory. So one of the things, I'll slide back over here. So I should definitely show the references, but you can use mod scan and to scan for kernel level drivers. So that's a whole different topic altogether, but there are plugins within the Volatility framework that will help you look for kernel level rootkits, even though they seem to be more rare in my experience, but maybe not in others. I tend to come across more userland, process injection.
All right, thanks. This next one says they think you should really be using parallel 1 and or a RAM disk to speed up your volume 3 queries. Thoughts on that?
Nope, you definitely could. There are definitely ways to speed up Volatility 3 for sure.
All right, thanks. Can you map back a file handle to the process? For example, which process have to handle to cmd.exe?
So, I mean, you can, if you can map, so if you run the handles plugin, and then you, with Volatility 3, you would have to grep for capital file or case insensitive, and that is going to show you all file objects, all handles, file object handles that particular process would have. So if you were, if I understand the question right, so if you're looking at cmd.exe, you could run the handles plugin, and in this case with Volatility 3, you would have to grep for capital F for files, and that would show you all kernel or all handles to kernel file objects for that particular process.
All right, thanks. What kind of cases do you need malware analysis?
What kind of cases?
Yes, that's how it's phrased. It says, what kind of cases do you need malware analysis? And we can ask this person to,
Yeah,
explain.
I'm not really sure what the question is, actually.
Okay, all right. Well, let's give, that was our last question submitted, so let's give them a moment to see if they want to give us more information. In the meantime, please remember that a copy of the slides and recording of this webcast will be available for viewing later today and can be found on the SANS registration page. Okay, so I'm not seeing further clarification. Do you have any closing thoughts you'd like to share?
No, I just appreciate everybody's time. Hopefully that wasn't too much, and I really hope that my dog wasn't too loud in the background.
I didn't notice anything distracting, so I think you're fine.
Oh man, she really wanted let out.
You've got a couple of feedback, people saying great presentation. Someone else says another brilliant presentation, Aaron. Thanks for demoing, editing the file to remove the leading bytes in the hex editor. Great pacing and very clear explanations. So,
Good.
Okay, great. All right, well, thank you so much, Aaron, for your great presentation, which helps bring this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, please visit sans.org/webcasts. Until next time, take care, and we hope to have you back again for the next SANS webcast.